The question might arise, why is a polymer physicist heading up a center for data science? Well, the standard answer I give really is that I'm a statistical physicist rather than a polymer physicist, and statistical physics is all about information theory, data science, very closely related. And then over the last couple of weeks, I've been thinking about it, and I've realized actually that from the condensed matter group at Oxford of 4 people, 3 of them have given rise to colleagues who have gone on to head up data science centers, me one, but also our sister data science center in Deakin is headed up by somebody who is in the same group as me at the same time, even though we didn't meet. And a very good and large data science center in Finland is also headed up by a condensed matter theorist from Oxford. So clearly there must have been something in the water in Oxford that pushed us to head up data science centers. As I said, I don't identify myself as a polymer physicist, more as a statistical physicist. And I think you'll see the difference and the reasons during the slides. So I'm just going to talk very briefly about what my research is, all the different things that I'm interested in, keywords, and then I'm going to get into the talk proper. And I'm going to start talking about random walks in one dimension and something that you'll find on the internet as the drunkard's walk, where a drunkard tries to avoid falling off a cliff, which of course the rest of us would normally find easy to do. I'm going to show you how that simple model actually, with very simple changes, becomes quite relevant to all sorts of problems in statistical physics. From the 1D realm, I'll move on to the 2D and 3D realms, random walks, and talk about my research about polymers in solution. Then I'll go on to polymer translocation and finish up with the current work that I'm doing on polymers, and I'm specifying on polymers because I am diversifying the work that I'm doing now that I'm back to research and back in a research center. So what's my research all about? Well, it's equilibrium and non-equilibrium statistical mechanics, which sometimes in the university gets one called a statistician. You should think more about thermodynamics and not statistics. The statistical in statistical mechanics is a little bit of a misnomer. And in particular, phase transitions and critical phenomena. My application area is soft condensed matter and polymer physics. And in particular, I spent a lot of time looking at the mathematical entity known as self-avoiding random walks. But more generally, these things fit into Markovian processes, stochastic processes, and things I'm moving on to now relate more to systems biology and stochastic epidemiological models, which sounds quite different, but actually there's a common routing. And other keywords, information theory, probability theory, optimization, complex systems, modeling and simulation are all identifiers for the research I do. The photograph, after some thought, I decided to dedicate this talk to Pierre-Gilles Degene. The 2 big influences in my field are Degene and Michael Fisher. Michael Fisher's, I believe, is still doing well and still active, but Pierre-Gilles Degene is no longer with us. Nobel Prize winner for his work in polymers. And I think what's notable about him is that he developed both theory groups and experimental groups and showed that fundamental theoretical physics can have very clear applications. He worked on polymer physics, adhesion, wetting, and all sorts of very practical problems. So the drunk walking along a path, imagine that somebody has had a little bit too much to drink. He's near a cliff, and he knows that if he goes over the cliff, he'll fall and he won't be very well. But because he's drunk, he can't really help staggering towards the cliff occasionally. But he has common sense, so he tries to stagger away more often than he staggers to. So imagine a walker, he steps 1 step away from the cliff with a probability P, and he steps towards the cliff with a probability Q, and P is hopefully greater than Q. if you do the calculation, you can see that no matter where he is along that path, no matter how far he is from the cliff, sooner or later, he will actually get to the cliff. As long as Q is bigger than 0, there will sooner or later be the rare event that he gets to the cliff and he falls off. So the probability that he'll fall is 1, and it's not something that I'd recommend trying. You know, mathematically, it's not very difficult to solve. I think you can find a solution on the internet quite easily. And you can imagine the local council, particularly once the pubs reopen, you know, they don't want to lose too many customers over the cliff, and so they install a handrail. And the effect of this handrail is obviously that the person will bump on the handrail, and it will tend to push the average position of the walker well away from the edge of the cliff. So you might ask, well, what is this to do with polymers and thermodynamics? And I'll come to that in a second. But the effect of the drink is to make this walker walk randomly to left and right. And the effect of that is that the system defined by the walker is what we call ergodic. And ergodic simply means that he will visit every configuration, every site with the appropriate probability given enough time. And this is a very important principle in statistical mechanics, this ergodicity. And here, this ergodic, this random motion, is influenced by drink. In thermodynamic systems, it's induced by Brownian motion and by temperature. An important thing that we'll come to in the next slide, the number of visits to the barrier, while the number of visits to the barrier will be infinite, no matter where you start the walker along the line, the proportion of visits to the handrail will be 0. So we're looking at rare events, but rare events happen. And in this box, I thought, well, since we're all locked up due to COVID, we're all in our home offices or living rooms or wherever, it was important to make a connection to pandemics and epidemics. If you imagine that, you know, this drunken person is going to drift away from the barrier, and he's going to drift at a particular speed, and that speed is just going to be given by P minus Q. So after T steps, he's going to be P minus Q T away if he's sober, because he's going to walk away from the cliff. If he's been drinking, then he will on average be the same distance, but he'll stagger to the left and to the right. And as we've seen, there's the possibility of a rare event that he falls off the cliff. Now, the position of the walker can be thought of in an epidemiological model as the average number of infected people in a very simple model. And you see that a deterministic model will give you a steady state or a nice drift away from no infections. Whereas if you have a stochastic model of epidemics, particularly in small populations, rare events will happen, and often a stochastic model will predict that the disease will extinguish itself by one of these rare events. So rare events can be very important. So if I now change my time into an x-axis and I think about my walker stepping away from the cliff in the y direction, so I get these little triangles as I move in time, then I can think of this as an interface. And I can imagine that under the interface I have water, and above the interface I have air, for example. And every time the interface touches the surface, it sticks. You know, maybe there's a bit of honey on the handrail, it sticks, and there's a particular energy of attraction, which is epsilon. And for it to be attractive, epsilon has to be negative, so it gains energy by touching the surface. But I'm going to denote this by a weight, omega. Weight's going to be related to a probability, and every time I touch the surface, I'm going to get a kick, an energy gain. But if I'm stuck near the surface, I'm going to reduce the number of configurations, the number of ways I can draw the surface whilst being pinned close to the wall. So in the same way that when I put a handrail up, the drunken person would be pushed away from the handrail, this interface is going to be pushed away from the surface. It would actually like to be far from the surface, but on the other hand, so that's maximum entropy, but on the other hand, the surface is sticky, so it has an advantage to touch the surface and be glued to the surface. And this competition is what gives rise to phase transitions. And in this particular case, the phase transition that we're looking at is a wetting transition. So when it's stuck to the surface, you can see that it has these drops, and these drops don't necessarily run, and that's for large omega, low temperature, so that's the dry phase. And then if omega drops below a certain level, so it's not sticky enough, we enter into a wet phase. So I'm just going to define something for later. So if I look at all the possible walks of length n, they're all going to have their own individual probability of occurring. And this probability is going to be proportional to omega times the number of contacts. But we need to normalize this with a coefficient, which we call z, which is called the partition function. And z is something that we'll discuss briefly later on in different contexts. So it's just the normalization constant. But for those who know thermodynamics, it's also a measure of the free energy. And the free energy is this balance between the stickiness and the entropy. When I interview people for jobs, one of the questions I ask them is, can you tell me about a piece of research that you're particularly proud of? And 9 times out of 10, people say the last paper they published. That's the thing they're most proud of. And I'm just going to talk a little bit about this particular model, which is related, because it was the very, very first paper I published. And it's the piece of research I'm particularly proud of. So here we have a similar model. Yeah, pointer works. A similar model, whereas now I can, instead of stepping just one step to the left or right at each time step, I can move as far up or as far down as I like. Whenever I touch the surface, I get my little energy kick. But we're just introducing another energy, which encourages folding. So I get a little energy kick whenever the 2 lattice sites next to each other are occupied. And this is a model of a polymer collapse, directed model. It's a particularly simple model. And numerically, it had been very, very well studied before I started my thesis. And in fact, it wasn't a problem I'd been assigned. It was my predecessor's problem. But being bored with what I had been given to do, I started thinking a little bit about this and realized that I could actually solve exactly for this phase boundary. So this phase boundary is between a collapsed polymer and a polymer that's stuck to the wall. And numerically, it had been known very well, and a friend of my PhD advisor had managed to actually get the exact solution by using a calculator and just fitting. But as I say, within a few months of starting my PhD, I managed to get this piece of this result out, which was something much better people than me had not yet managed to do. So I was quite, well, I am still quite proud of that. One of the key things in physics is that we like to make analogies, and we like to pinch techniques and ideas that we see elsewhere. And so it's important to recognize these analogies. And an interesting analogy between 2-dimensional statistical mechanics is with 1-dimensional quantum systems. And the wetting problem that I've shown you is actually completely equivalent to a problem of an electron being bound inside a potential well, as long as we take this potential to be a delta potential. If epsilon is small, then the electron doesn't bind, it moves away from the well. And if epsilon is large enough, larger than some critical value, then the electron is bound. Those of us who've done quantum mechanics know that in a finite well, there are many bound states, but in this particular delta case, there's only one possible bound state. So I guess the takeaway from this first part is that whereas the original model of the drunken walk is simple, small modifications make it more physically relevant and mathematically interesting. And when you actually try studying these things, they can lead into some very interesting mathematics as well. So having looked at one dimension, we should move on to more physical dimensions. And the term random walk was first used by Carl Pearson in Nature in 1905. Now, I have a very strong memory of sitting in the Bodleian Library reading the Proceedings of the Royal Society 1898. There was a paragraph in which somebody talked precisely about the problem of drunken walker in 2 dimensions. How would he get home? How far would he be from his point of origin? But random walk was first coined in 1905. And Carl Pearson actually published an article in Nature asking the readers to solve his problem for him, which is not something we would think of doing now. And the problem he wanted to know was, what's the probability of being a distance r from the origin after a certain number of steps? And that's quite a difficult problem, but a much simpler problem is how far on average is the walker from the origin after n steps, assuming that each direction is allowed with equal probability. So I don't have a bias as I had before. I stagger in any direction I want, 1 unit length, and I can make life a little bit easier by looking at it on a square or cubic lattice. But essentially it's the same. I start at the origin, I pick a direction at random, move a step, and then I pick another direction at random. I don't mind if I've been there before. I can walk back on myself. There are no restrictions whatsoever. And the question is, what's the end-to-end distance on average after n steps? And the result is that r goes like n to the half, the square root of n. It doesn't matter whether it's on a lattice, off a lattice, 1D, 2D, 3D, 4D, 5D, it doesn't matter. If we now imagine that at each step, we place a little pebble, as in Hansel and Gretel, then the mass of the polymer is just n plus 1, because we started at the origin times the mass of the pebble. And we can use this example to show that for n large, the mass then goes like r squared. So it's the inverse of that half. Now, if you think about it for a little bit, if I have a rod and I double the length of the rod, then I double the mass, and it goes like the length. If I have a disk, it goes like the radius of the disk squared. And if I have a sphere, it goes like the radius of the sphere cubed. So this scaling of the mass with a linear distance is a dimension. And in this case, it's the fractal dimension, which is known as the Hausdorff dimension. And the fractal dimension of the random walk is 2, again, regardless of dimensions. So what's the relevance to polymers? Well, if I look at a photograph of a polymer, a long polymer in solution, it looks pretty random to me. Everything I do is going to be in the limit of large n. And you could reasonably ask, is that limit reasonable in biopolymers? Are biopolymers really got lots of steps? Well, if you consider that a DNA molecule unwrapped and held out is about 2 meters long, then you realize that there are biological polymers where these things are very relevant. So it looks like a random walk, but if I can measure its not so much its end-to-end distance, but I can measure its linear size quite easily. I've got the hydrodynamic radius. The hydrodynamic radius is where I put the polymer in a flow and I hold it, and I measure the force acting on it, and I apply Stokes' law as if it were a sphere. That gives me a measure of the radius. And the radius of gyration, Rg, which is just the average distance of the polymer from its center of mass. And this comes out from neutron scattering experiments quite nicely. And what we find is that in 2 dimensions, this exponent is 3/4. So the dimension is the inverse of that, 4/3. In 3 dimensions, it's 0.58. And 4 dimensions and above, it's the half. So I only get a random walk in 4 dimensions or above, but I don't in 3 dimensions and 2 dimensions. And what's interesting is when you do these experiments, and this is the wonderful thing for me, is that the results don't depend on the chemistry. I didn't particularly like chemistry at school. So it's all physics, it's no chemistry. It doesn't depend on the fine details of the interactions. It only depends on the range of interactions and the dimension that you're in. So why do we not get random walk behavior? And there's a very simple argument. If you imagine that a random walk is 2-dimensional, then okay, so if I have a polymer is made up of monomers, and the standard argument is that monomers have a size, and so you can't put 2 monomers in the same spot at the same time. So you get what we call a volume exclusion interaction, which is made worse by entropy. So the random walk is essentially a 2-dimensional plane. The monomers have a finite volume, but if 2 bits of polymer don't see each other very often, then they're not going to interact very much, and we're not going to get very much of an effect. If you think of a 2-dimensional plane in 2 dimensions, so what I'm going to do now is I'm going to consider 2 bits of the random walk that are very far from, they're connected, but they're portions that are very far from each other along the chain, and I bring them into contact. Well, in 2 dimensions, if I have a 2-dimensional plane and I put another 2-dimensional plane, all the points are going to intersect. And so any interaction there are between the visited sites, the monomers is going to be very important. If I look at 2 2-dimensional planes in 3 dimensions, then those 2 planes in general are going to intersect as a line. A line is going to involve an infinite number of points, and so there's going to be an infinite interaction, which is going to tend to push the 2 parts of the polymer away. In 4 dimensions, 2 2-dimensional planes are going to intersect at a point. A point is singular, and therefore it's going to have very, very little effect on the whole polymer as a whole. And above 5 dimensions in general, 2 2-dimensional planes won't meet at all. So you see there's a change in the number of times the walk is going to meet itself and therefore interact with itself that becomes quite drastic above 3 dimensions. And that's why above 4 dimensions and above, we see random walk behavior, and below 4 dimensions we don't. And this is being looked at experimentally and verified. It doesn't depend on the chemistry, as I said, and this gives us the notion of universality. And the notion of universality tells us, well, actually, all we need to do is look at a minimal model that has the same basic ingredients, and we should see the same basic physics. And that motivates us to look at lattice models and not worry about the continuum. The other effect that we have in real polymers is the quality of the solvent, which can be changed either by adding salt or by changing the temperature. And this can be modeled very simply by looking at little energy gains when 2 lattice sites that are nearest neighbors are visited. And I represented this again by what we call a Boltzmann weight, an unnormalized probability, which is just the exponential of the nearest neighbor energy over KT. And it's attractive again, so the energy has to be negative. So if this attractive energy is small or the temperature is high, then the polymer won't stick very much to itself. It'll be much affected by Brownian motion. It will swell out, and we'll get the behavior that I mentioned in the previous slide. That's what we call a good solvent. And if this tau is big, correspondingly the temperature is small, then we have a phase transition into a bad solvent. The polymer will then collapse in on itself and in practice precipitate. So when the polymer is in a bad solvent, its dimension is going to be the same dimension as the spatial dimension, and the polymer is going to fall out of solution. But when it's in good solvent, so as it's going to have the behavior I mentioned before, and as we transition at what we call the theta point, the transition point, we have new critical behavior, new fractal dimensions for the walk. So the radius of gyration goes like n to the 4/7 in 2 dimensions and n to the half in 3 dimensions or above. Now you could reasonably ask, is it physically relevant to ask this question in 2 dimensions? And I can reassure you that experiments were done in 2 dimensions where polymers were floated on the surface interface between two solvents, and the results were convincingly found by one experimental group, but other experimental groups couldn't quite find the same accuracy. They could only say that this exponent mu was bigger than 0.53. So 0.56 is actually pretty close to 4/7. So note that 4/7, that means a fractal dimension of 7/4, which is less than 2. And as I said, this behavior is expected to be universal. If I look at a very, very long walk on a big lattice and I look from a long way away, I start losing the details of the lattice underneath, and I just see something that looks like a polymer. And so, whether it's on lattice, off lattice, the behavior should be the same. Unfortunately, things aren't that simple. And I published a number of articles between 2003 and 2018 for models where that is not the case. Doesn't seem to follow universality, and that's due to frustration effects. So we said it doesn't depend on the details. So in principle, if I get a kick, if I get my energy gain by close range interactions, even if they're on the same site, the walk is otherwise self-avoiding. It doesn't, exclude volume. You would expect to find the same behavior, and qualitatively you do, but at the transition in 2 dimensions, you find a fractal dimension of 2, not 7/4. And the argument is that precisely because that fractal dimension is 2, these interactions start competing with the lattice structure. And when you look at it from afar, you don't lose the details of the underlying lattice. And in fact, if you look at a triangular lattice or a hexagonal lattice, you will see different results. Okay. So moving on, so I want to talk a little bit about polymer translocation. And before we go on to polymer translocation, I want to talk about some work that I did in the mid-90s on hopping particles. This isn't my work, this precedes the work I did, but if you imagine a line, a one-dimensional lattice of sites, and these sites can either be occupied or empty, and if they're occupied, the particle that occupies them can hop forwards. So the dynamics is that I choose a lattice site at random. If it's occupied, then the particle hops forward if the neighboring site is empty with a probability P, and hops backwards again if the lattice site is empty with a probability Q. But here, for example, I couldn't hop forward because I'm locked by the particle in front. This very simple model is still being studied today. It's a model for traffic flow. You can also use it as a model for polymer gel electrophoresis, how polymers move under an electric field in a gel. molecular beam epitaxy, which is what I'm going to show you now, even biological motors, load carriers in biological situations. So we've been a very flexible and versatile model. And to look at the surface growth of molecular beam epitaxy, if you imagine that the slope down is denoted by a particle that's a site that's occupied, and a slope up by a particle that's empty, the deposition of a square corresponds to a particle jumping forwards. And the evaporation of a square corresponds to a particle that's jumping backwards. And we feed the lattice with a particular rate alpha at the entrance, and we remove particles with a particular rate beta at the other end. The model I looked at corresponded to two different types of molecules, particles, some particles going that way and some particles going that way, with a particular rule about exchanging the particles. And that had some very nice symmetry breaking properties, which we thought at the time we were the first to see, but it turns out that actually in computer communications, packets coming into a computer, if you have single line of packets coming in and packets going out, and you have particular rules that allow some in and some out, you actually get the same sort of behavior. So moving on to polymer translocation, and the slide that I showed earlier will become relevant in a minute. So there's some very, very nice experiments where you can pass polymers through what we call a nanopore. So a nanopore is just a nanometric pore, most commonly a molecule called alpha hemolysin, which is the toxin in Staphylococcus aureus. It's a nice molecule that self-assembles, punches a hole in the membrane of the cell, and then the cell empties out. In this particular case, you coax it into punching a hole in a lipid bilayer, soap film. And what's nice is that you can get it to punch one of these things to punch a hole. So you've got a very controlled, well-known sized hole in a lipid bilayer. You pass an electric current through it, and you can measure the current of ions going through this pore. And now what you can do is you can put a protein or a DNA fragment or something in this side, in the cis side, and it will move through the pore. And whilst it's in the pore, it will block the pore partly and will cause the current to drop. Now, the idea and the hope is that if you can get the polymer to go through, to translocate slowly enough, then you should be able to analyze this signal, and in a good circumstance, you should be able to identify the monomers that are sitting within the pore. So it raises the hope of fast sequencing of DNA, for example. And so the whole trick was either to create artificial pores or to use these biological pores to slow down the passage of polymers and to see what the signal is and try and interpret what's going on within the pore. Very active at the moment is to use machine learning techniques to differentiate the different sequences. And there's a research group, Hagen-Bailey's group in Oxford, that's been very successful at this many years. And they had a spin out a number of years ago called Oxford Nanopore. And if you looked at the Telegraph a couple of days ago, they're talking about possibly floating Oxford Nanopore on the market, and its estimated value is 16 billion. So unfortunately, they're not my collaborators, but it does show that this technology could have a ref impact and possibly more. And the reason they're valued so highly is that they've managed to sell kits that people can use to fast sequence COVID-19. And probably the reason why we have so many variants in the UK compared to other countries is that we're very good at sequencing quickly, possibly partly due to Oxford Nanopore's work. So coming back to polymer translocation, the hopping particle model, for many polymers, you can approximate what's going on within the pore as a single file passage. And we had this idea a few years ago. There were some nice experimental results looking at the time of passage of polymers depending on their length. And there was this peculiar behavior at the beginning of the, for short polymers, that wasn't really very well explained. And the two methods that existed at the time was either the Fokker-Planck method, where you approximate the center of mass of the polymer as moving in a complicated potential well, but that's too approximate and doesn't see the collective behavior. Or molecular dynamics, where you do an all atom simulation, and they tend to be very, very, very slow and only simulate a few nanoseconds of dynamics. So we wondered whether we could, at least in qualitative terms, reproduce the same behavior. And our idea was to look at the dynamics within the pore as an asymmetric exclusion process, a hopping particle model in 1D. And then this feeding rate, alpha, is determined by the average behavior, the approximate behavior of the number of monomers that's left in the input region, in the cis region. And the beta, the rate of pulling particles out the other end, is modeled by the number of monomers that are found in the output region. And we found quite good qualitative agreement between our little numerical experiment and the true experiments. Whereas molecular dynamics might take weeks or months to do, our little simulation took of the order of 30 seconds, 30, 40 seconds. So it would be, not as good as an exact solution, but not bad. So what am I currently doing? What am I currently looking at? Well, we're looking at a model of DNA. So the difference between DNA and the polymers that I was talking about before is that they only stick if two monomers the same distance from the origin come together, otherwise they ignore each other. In this particular model, we were looking at random walks, and they stick to each other if, as I say, if the amount of DNA from the origin to the point of contact is the same. So here we only have two interactions, one here and one there, because the distance is right. All the other times the polymer meets, the distance are different, and therefore there's no interaction. This is to model the base pairing that happens in DNA. And we're looking at three-stranded DNA, which does exist in nature. It's not very common, but it does exist in nature. And we're looking at it as an analog, a biological analog of three interacting quantum particles. So if you have three fermions, for example, if you have two fermions that won't bind to each other, they're just on the point of being unbound, then what happens is that when you bring a third one in, it will often form a triplet, a bound triplet state. And if you're at the right point, that's called the Efimov phase. And it has a very special scaling behavior where there are an infinite number of bound states that are equally separated in energy. And that translates into a particular scaling form of the free energy. So if you think of the length along the chain as time, and when they touch as an attraction between the particles, and then you see that they interact at equal time, which is the same as the quantum particles would do. And the quantum analog here would be that if this interaction was too small for two chains to bind, then putting three chains might form a triplet that binds together. In this diagram, I'm just showing the scaling of the free energy. And the green line is what would happen if we didn't have this Efimov behavior. See, on the big diagram, they both look perfect, but if you look at small n values, see that without this Efimov phase, we get the green line. With the Efimov scaling, we get the red line. the black points are our simulation data, and we get very good fit, very good behavior. And the other thing that I'm looking at the moment, just finishing off a paper on magnetic polymers. So very few polymers, the monomers are neutral. This was a model from '99 that they looked at quickly in 3 dimensions, and the idea is that you just have magnetic moment on each monomer that can be up or down. If they're pointing in the same direction, there's an attraction. If they're pointing in opposite direction, there's a repulsion. There's no other interaction energy. There's no solvent to take care of at the moment. We might add that later. And the question is what happens? So the only energy we take into account is the magnetic energy. For those who know, this is just the Ising model. The Ising model doesn't have a phase transition in 1 dimension. It does in 2 dimensions. So there'd be no magnetic ordering if the polymer is extended. But if it were to collapse on itself, there would be. And what's found is that there's a simultaneous collapse and paramagnetic to ferromagnetic phase transition. And what's interesting is that this is quite different in 3 dimensions to 2 dimensions. And we're looking at the difference between the two. It's surprising sometimes what's the interesting maths. In this particular case, we're looking at various methods to study this phase transition, but something that I learned from a colleague at Coventry, who will know who he is, was that actually the partition function, which is just this normalization constant, is a polynomial. So here I've just taken out a factor corresponding to the maximum unfavorable contacts that I have. This polynomial, and there should be a coefficient there that I forgot, so there's a coefficient. All those coefficients are positive. As you know from your high school maths, a polynomial with all positive coefficients doesn't have a phase it doesn't have roots along the real positive roots. But if you look at the complex roots, you can have information about the phase transition. And just as a pretty picture to finish up with, those are the complex roots for this model in 2 dimensions and 3 dimensions. And Ralph, if you're in the audience, you can email me later to tell me whether you can tell just glancing which is first and which is second order. But otherwise, I'll look at it more closely. So just a list of collaborators that I've had over the years. I've also listed people whose scientific advice and personal advice was very important to me over the years. I should just finish up saying, when I went to Oxford, Oxford was unusual at the time that they didn't take you onto a specific PhD project. They took you onto a cohort and then you had to choose your project later. I wanted to do the neural networks. I didn't want to do this gloopy stuff called polymers, and I ended up drawing the short straw. I ignored the quantum field theory lectures because I thought they wouldn't be relevant. And all I can say is that Julia, my thesis advisor, said, don't worry, all research is interesting. And I've had a whale of a time ever since, and regretted not knowing the quantum field theory because it is actually very relevant to polymer physics, believe it or not. So thank you very much.
Damien, thank you very much indeed. That was an absolutely fascinating talk. I've certainly learned something. I hope that's the same for everybody. I'm going to throw the floor open for questions, and we've had one posted in the chat. And Damien, I think it's fair to say that this is quite a detailed one, because I'm not sure that I would want to get this one. So in the random walk lattice model, what will happen if we get the Hausdorff dimension an integer like 2 or 3? Is it going to be a space-filling lattice?
Okay, so the Hausdorff, the Hausdorff dimension is the fractal dimension. So It will only be space filling if the dimension of the walk is the same as the dimension of the lattice. And that's what made the frustrated walk models interesting, is that the Hausdorff dimension and the lattice dimension were the same. And so it was space filling, and therefore you couldn't ignore the underlying lattice. In general terms, the Hausdorff dimension will be lower, in which case that means that you've got a good continuum limit, and it's not space filling. I think that's the answer to the question.
Well, I'm not going to contradict you, believe me.
Thank you. That was brilliant, Damien. My question was, when it becomes space filling, what will happen to that? I think implementation of that kind of, implementation of that polymer.
Okay, so there are models that are space filling. They're called Hamiltonian walks.
Right.
And they're a pain to do by simulation. You have to do them in other ways, which you can do. And what becomes interesting then is if you look at rigidity. So you look at adding an energy for a corner, and you have a very interesting phase transition that happens when the bending energy. So if you don't allow bends very easily, there's a transition where you have a nice corrugated walk that fills all space, and then that energy becomes too stiff. The polymer becomes too stiff, and it just ejects all the corners to infinity, and it becomes a crystalline structure.
That's brilliant. That's brilliant.
And that's for those who know, it's actually an infinite order phase transition, which is unusual. So first order is a transition with a latent heat. Second order is with a diverging specific heat, and an infinite order, we don't really know what it is. You know, it's nothing really diverges, but there is a phase transition.
Brilliant. Thank you very much. I think showing how the random walk linked to fractal dimension was really interesting for me. Thank you. Thank you, Damien.
You're welcome.
Can I also ask something? Hello.
Oh, of course, Nikos.
Please do.
Yeah, thank you very much for the nice talk. I just want to ask something about the magnetic polymer stuff.
Yeah.
Maybe you know, like many years ago, the French people from Saclay, I think, you know, Garel and Orlan and so on.
That's the 1999 article I was referring to. Yes.
Okay, yeah. So they did this mean field. They transformed them in 3 dimensions. They solved the model in the mean field using a Gaussian model, and they actually, in the Hamiltonian you wrote, I mean, they also had some kind of external magnetic field, because they found, I think, that they could actually tune the collapse transition, you know, by changing the ferromagnetic short range interactions. So
what happens in 3 dimensions, the transition's first order without a magnetic field. What they showed, unfortunately, Monte Carlo's come a long way since. What they managed to show is that if the magnetic field is high enough, you get the normal bad solvent, good solvent behavior that I was talking about.
Exactly.
What they couldn't do is they couldn't find where that change of behavior happened, and it's very difficult. In 2 dimensions, you get a second order phase transition. You don't get, it changes behavior immediately, that I can see. And the transition, the combined collapse magnetic transition has the Ising exponent. So it's quite different in 2 dimensions. And interestingly, if you look in the literature, somebody used the fluctuating bond model for the 3-dimensional case, and they also find the second order phase transition with the Ising exponents. So there's something that 1999 paper was very good, but it was just the start of the story, and I think there's more to say.
Right, but I just want to say that, you know, in terms of Monte Carlo simulations, not much has been done actually. And most of the people did consider, you know, just standard Ising ferromagnet, when in principle, you know, you could think of having like maybe long range ferromagnetic interactions, or maybe next nearest neighbor stuff, which makes the problem like more realistic. So practically not much has been done in numerics. That's what I want to say.
Yeah.
Okay, thank you.
Cheers, thanks.
Anybody else?
I think as a leaving message, what I'd like to say is that what's nice in statistical physics, and if you look at statistical physicists, they wander off and do all sorts of things like you know, sociophysics, econophysics, goodness knows what else. And I think it's this idea of connections. We're magpies. We like to see the same maths in other problems and reuse it and pinch from other people's work. So the number of times in a seminar about something quite different, I've spotted a technique or a method that I could use for one of my problems. I think that's the fascination with this field for me.
Thank you very much, Damien. So on behalf of everybody here this evening, I'd like to reiterate my thanks for Damien for a fascinating talk. Damien, thank you very much indeed.
Thank you.
I'd like to wish everybody a good evening and look forward to seeing you at the next lecture in the series. Thank you very much.
Thank you.